break. And then we need to move now to the last speaker of the session, that is Alexandre Chikahoui, business developer and director of X-Celeprint, who is going to talk about micro transfer printing technology and applications to photonic integration. Thank you.
So, good morning, everybody, and thank you very much for the invitation and the opportunity to talk here. I'm Business Development Director at X-Celeprint, and I'm going to talk to you about the application of our technology into the silicon photonics or photonics in general applications. Before going into the detail of the technology, I just would like to introduce our company for those who are not really aware about it yet. So we are headquartered in Cork, Ireland. We have a fully owned subsidiary office in US, in North Carolina. We're about 20 people, and we're an R&D and technology company. And we're developing microtransfer printing. That's what we are going to talk about today. And we have today about 249 patents issued. And it is very expensive to maintain those patents, but this is also our main business, which is licensing. So we're licensing the technology, and whoever licenses our technology to us will have access to all those patents. The other business we're doing also is spin-off of new businesses, and I'm going to mention that to you a little bit. So I'm going to go quickly through the history. I'm not going to go through each of the points, but the main message is that the microtransfer printing technology is available since year 2000. So you're talking about almost 20 years availability. It has been created and invented by the professor John Rogers in the University of Illinois. And that technology has already reached mass production in 2010. Into the field of concentrated PV cells for solar panels. So this is already into production, and when that production started here by a company called Semprius, this is where X-Celeprint was created back in 2013, and the purpose of X-Celeprint was to try to license the technology and to go into production on other fields than concentrated PV cells. And at that time then, we were working very hard on a new application, which was the micro LED displays, and all our resources were focused on trying to create the new technology that would compete with OLED displays. It took about 4 to 5 years to come to some results, and actually, this is something that happened. Doesn't work. Okay, so this is something that happened in December last year, so just 1 month ago. We succeeded to successfully spin out and get funding for a new company that is existing since last month, which is called X-Display, and which is going to manufacture and build product. It's not going to be doing licensing. And X-Celeprint still do exist, and is going to concentrate on licensing of the technology, but on any application except display applications. So, and as I said, our business is to do also spin-off of other companies, and I'm working on new applications where we are already seeing that we can build products, but we cannot tell right now what we are doing. But this is always related to very, very, very small components and packaged components. So, about the technology itself, what is microtransfer printing? So basically, it's the ability to transfer any sorts of components, which is indium phosphide, gallium arsenide, silicon ICs, any sorts of material to any sorts of substrate, right? And so a lot of people will tell us, well, okay, but then it's pick and place, right? Well, yes, it is, because we're just transferring components to different type of substrate. But I really wanted to quickly tell you that our technology and pick and place are really not comparable and are in order of magnitude different. So when you think about pick and place, the smallest components ever they can handle is 120 by 120 micron type of components already. You're talking about thicknesses down to 100 micron, and the transfer speed is about 25,000 components per hour, and with an accuracy of 10 micron. When you look at the pick and place roadmaps, and this is information that you get, how you get them, basically. You succeed to get those information. They are already thinking about going down to 50 by 50 micron and with 20 micron thicknesses, with definitely not yet 25,000 transfer per hour, neither the same accuracy. So where we are with transfer printing today. So today, and without any efforts, we can already transfer components as small as 2 by 2 micron. So it's already order of magnitude smaller than what pick and place can do. And in terms of thickness, we can transfer down to 0.5 and up to 20 micron thick components. And in terms of the transfer speed, instead of the 25K per hour, we can do 100K, but not per hour, but per minute. So again, it's an order of magnitude different with an accuracy on 1.5 micron. And in terms of microtransfer printing tomorrow, well, we can go smaller, but frankly speaking, today we don't see a need of going smaller. There is some particular markets where you need to transfer something less than 1 micron, but this is not our priority. We can go very thin, and we are targeting 200 nanometer transfer. For information, we can already transfer aluminum or gold membrane, so very thin metal. So there are some applications requiring the transfer of thin metals. And in terms of transfer speed, we are targeting the 1 million pieces per minute. So this is needed for displays, but also in silicon photonics, for some customers, the throughput is extremely important. And so this is where we are heading to. And the accuracy, of course, and in silicon photonics is very important. And we are reaching, we haven't published it yet, but we are reaching things which is much below 500 nanometer accuracy in placement. So pick and place and transfer printing is not competing technologies. It's order of magnitude different. It's just different field. And this is kind of summary I try to do is, for whatever is below a square millimeter in size, use transfer printing. For whatever is thinner than 20 micron, use transfer printing. Above, this is not our world. We are not competing in that. So the other benefit of transfer printing is that it's a true heterogeneous integration. Here is an example of what we did on displays. We were targeting very, very specific displays, not just competing against existing displays, but this is a display where you have an active CMOS chips connected with micro LEDs. You have a gallium arsenide magnetic sensor, as well as an indium phosphide HBT device. So displays will be really different in the future, will be sensing magnetic field, so that's really depending on many applications. And this is what you can do, and this black square you see here was made black for the picture, but it's onto a transparent display, right? And what you see here is just 1 pixel. So the size of it is just 300 micron on the side. So how do we do it, right? So the first thing we do is, when you have your wafer, we are going to undergo onto that wafer some MEMS processes to make sure that the devices on those wafers are rendered like floating, and like you see on this picture on the bottom right. So the device will be floating and held by a tether, which is connected to the anchor. So in that stage, the device is floating, and a small force only is enough to pick this device and to break the tether that you can see here. So this is the first part of our technology, is how to make this wafer transfer printable, we say, with floating devices. And so now you can see that the device is in the range of 1 micron thick. It's very small. So how can you pick it? Can you pick it with a needle, with a metallic needle? No, it will destroy it. It's too fragile. So you need it to have something that can be picking those devices without damaging them, and that has enough strength to pick them and break the tether. And this is really the core IP of our technology. This is the PDMS stamp, right? And we're using the viscoelastic characteristics of that material so that the molecular bonding between the stamp and the devices on the wafers when they're in contact are extremely strong. So when the stamp is removed quickly from the wafer, the tether that I've shown you before is breaking, and that's why the part can be removed from the wafer. On the contrary, when you're transferring the devices onto the target substrate, the molecular bonding between the device and the target are much stronger than the one between the stamp and the device, because now you remove the stamp very slowly. So this is the viscoelastic characteristics of the material that we're using. So the stamp features, it's compliant in Z directions because we have those posts, which are maybe 40 to 50 micron tall. So that means that we can handle any sorts of surfaces. It doesn't need to be super flat in terms of the wafer flatness. It's laterally stiff, which means that you have a high accuracy in placement. It's transparent, which means that now you can go and see through the stamp and you know where you can pick your components. And for those who are interested, I have a stamp with me. So if you want to have a look, don't hesitate to look at it after the talk. And it's also soft, and because then now it can handle very thin and fragile devices. The stamp can be very small. The pick head can be very small, but can also be very large. And the largest one we have made so far is a 6-inch stamp, which can handle and pick in one time about 82,000 components. And the transfer yield, you're talking about 99.94% for that large stamp. And we have much higher yield when the stamp is smaller. So what I'm showing you here in terms of yield is actually the worst case. Maybe I should show you always the best, but that's the worst we can get. And how you make the stamp is you define a silicon master, right? So this is lithographically defined. You then cast this silicon master against, like you're molding it with silicone. And this is how you get your stamp. So it's very low-cost material. You're talking in high-volume production of stamps, below $100, and you can use this stamp more than 50,000 times. So for production, it's a very low cost. So I'm going to show you a video, real-time video of how the transfer operates. But now you can imagine the stamp basically contacting the wafer and transferring the components to the target. So it's really, really moving dense devices onto the source wafer and to have them dispersed into an arrays on the target. And you can control this dispersion by the pitch, which is then actually decided by the posts here. So it's the accuracy of 1.5 microns 3 sigma. And this is, again, the worst case. If you transfer 10 or 100,000 at the time, this is the type of accuracy you can get. If you're transferring few components at a time, like 500 or 100, we can get much, much higher accuracy. The yield is 99.9%, and we're talking about 6 million devices per hour, which was equivalent to this 100K per minute. So here is the live video. This is the source wafer of micro LED that you can see here. You can see that the components have been picked now by the stamp, then moving into the target. And when you're reaching the target, they are placed on the target, and the stamp is then removed slowly. Then the stamp is going into a cleaning phase. It's just a Scotch tape so that you remove all the dusts from the stamp. And then it's going back to the source again, and is going to pick the next 4 components that you see here. The field of view of the camera is only showing 4 devices, but this operation is now taking 10,000 devices in one pick. And now it's printing 10,000 devices. So the key thing is that it's really high throughput and very high accuracy. So just to give you a process flow example of what we have, I've shown you on the very first slide, how to make this process transfer printable. So you start with a substrate device. It can be indium phosphide. It can be gallium arsenide. And to reply to the comment from Michael of Ligantech, yes, you need to have a release layer. Yes, it's not standard. And yes, I had the same worry about is it going to work or not. And the outcome is, and I can say it after so many years working with many customers, is that all our customers can include the release layer without any issue. And not only high-end customers, which is like Osram, who is one of our licensee, but also with customers in Asia, which has much less capability and who are like tier 2, all have no issue including that release layer. So it's a very stable way to do it for a variety of customers. Then you go your 3.5 device layer, and what we're doing is that we're patterning this wafer to create your device, your lasers, your photodiode, or whatever device you want to pattern, your VCSELs. The next step is you're encapsulating them. Generally, we use silicon nitride, silicon oxide as an encapsulant, and this is where the tether and the anchor are formed on the wafer. At that stage, we are now releasing the release layer through aqueous etch, and then your device is floating. After you get your device floating, your stamp is picking the device, the tether cracks, and you transfer it to your silicon photonic platform in this example. So this is what we're doing. This is the same flow that you can see here on the next slide. And so especially for silicon photonics, right, you have a lot of different aspect ratios. You have aspect ratios who are more like a square, rectangle, or very, very long. So on the left, you can see like photodiodes. On the right, you can see like lasers. It can be DFB lasers. It can be all sorts of lasers. So it's not trivial to be able to transfer very thin and long components. But for instance, we can already handle devices which are 1 millimeter long or even 1.8 millimeter long and with only 20 micron thick. So I don't know if you realize the ratio, but it's like a spaghetti, right? So you need to be able to transfer that and not breaking it and to make sure that it remains flat on the surface. So those are all the issues we're undergoing when developing our processes. Here is another picture. On the left side, you see the laser onto the source. On the right side, well, actually in the middle here, you see when the laser is removed from the source. And what is remaining is those tethers that were holding the device before. And completely on the right here, what you can see is the same thing. It's the source of a photodiode, the source wafer, where the photodiodes are removed. And on the right side completely, you have 2 or 3 photodiodes which are not removed, so that you see the difference between where is removed and not. So this is very straightforward once your process is stabilized, right? And I really wanted to show you some of the issues we're facing. And I think that what Michael was saying is also true. There are issues going through all those processes. Stress is a big issue, stress management. Here you can see the picture of a laser. And if you're not handling the stress right, your laser can really, really, really bend. And even can bend so hard that the tethers are breaking even you finish the processing. And even before you finish the release, you will have some part of the indium phosphide which are still stuck to your source wafer. So it's not straightforward, and you need to make sure that you are really, controlling the process and having an optimized process for what you're doing. But the good news is, as you get a license from us, all this know-how of 10 years development is given to our licensees. So they don't have to develop new processes, and all the configurations, aspect ratios of all the sorts of material, all the processes are set, and our licensees just need to apply the recipes. So that's the good news of it, is that our customers don't have to go through that painful work of optimizing the process. Another picture of transferred lasers on the right, on top of wave guides. And on the right, you also see on the bottom the transfer of photodiodes. Our customers don't want us to show the picture of the full silicon photonic platform, so I had to find a picture just to represent where those lasers and photodiodes are coming from. So yes, we are heavily working on the transmitter and receivers of silicon photonic platform, and our technology is now going to be also soon in mass production for silicon photonics. Another example is the integration of, it's not about evanescent coupling only, it's integration of laser into a recess. So you can print your laser onto a recess or a cavity, and then you can perform what you call butt coupling. This is a paper which was written in 2016, if you can read it, and we are reaching accuracies of 1.4 micron displacement between the output of the laser and the waveguide. And this is also something we cannot show, but I can only say it, is that the displacement reached today is below 300 nanometer today. And so this is why also butt coupling is also feasible, and also in mass transfer. Not 1 million pieces, but much smaller arrays. In general, microtransfer printing does not impact the source component performance. Here is an example of some lasers that we have measured in terms of current and light power output before and after transfer printing and with temperature. And before and after, you have exactly the same performance. And so we have confirmed that onto ICs, lasers, and all the components we're transferring. The component capabilities are the same. So this is my last slide. This year for X-Celeprint, this is the year of expansion and industrialization. One of the issues of our licenses is that they need to have a place where they can start mass production. So large companies like Osram, they don't have any problem. They're licensee with us for about 1.5 years now, and they're going to go into production, and they don't need anybody to go into production. They can do it themselves. But for all other customers who don't have the facilities that Osram has, they need to have a pilot line. And we are now setting up the pilot line at our sister company, X-Fab, which is located in Germany, in Erfurt. They have a MEMS fab facility, which is not fully occupied. And so part of that MEMS fab facility is going to be a pilot line for transfer printing. It's not ready yet. Only the transfer of silicon chips, ICs are ready for mass transfer. And of course, they're getting ready for 3.5 as well. So now the production will be really feasible. And other things, which is also things that I cannot disclose in terms of names, but we had new licenses last year in the medtech field. So there's a lot of demand here of small components transfer. LiDAR as well is a license that we signed last year. And of course, silicon photonics, more than one customer is there. So we're growing. We are setting up our fab. And also something new, we were making tools before. Now we're not making any more tools. The tools is going to be made by our partners. So we're setting up partners. So what the picture you see here on the right is a microtransfer printer tool, which is the latest one. And this is the one that our tool partner is going to be handling, and also support our customer with. So, and hopefully this tool company will be ready within this year to help our licensees, and whoever institutes who needs a printer also could have access to those printers. Because to do R&D, you do not need a license from us. You can do R&D with a tool. You just need a license from us for commercial use. And that's it. Do you have any questions?
Thank you very much, Alexander. So if there are any questions from the audience? Okay, one question.
Well, first of all, congratulations. Truly fascinating. I'm amazed by what you guys are doing. Last May, I went to Regensburg and I saw the tool at the EPIC meeting on automation at the one in collaboration with Osram. Fascinating. For the micro-LED manufacturing, it's really great. Why is it taking a bit longer in the photonic integrated circuit community to adopt this than in the micro-LED manufacturing?
It's not taking longer. It's happening. It's just not public.
Okay.
Okay, so I think we should go all for the coffee break. And thanks, Alexander, again, and all the speakers of the session. And we will be back at 11:30.
Yes, I think we should be back like in 20 minutes, please, so we don't accumulate too much delay. Thank you.